All right. Okay. I hope this went well. I'm interested in looking at your answers. Okay. Yeah, before we switch on to the lecture, I just want to confirm that next week next Tuesday, there still will be a quiz. Even though it's the finals week, I wanted to do a quiz so that there's enough of them that the way of each quiz is not too important. So that plus the fact that I'm dropping the either miss quiz or uh, yeah, other miss quiz or your lowest grade, depending on if you missed the quiz or not. That way you'll have enough quizzes, so each quiz is not so important and has not so too much of a weight. Next week, yeah, there's a question asking about how much content are we covering next week. And so my goal, it looks like my goal is that we don't cover too much content. So probably only Monday we'll have new content because looking at the days we have left, I'll still need to squeeze something on Monday, but otherwise, I think that past Monday there won't be any new content, and then Tuesday I think would be just the quiz, and then I think we just don't do anything after the quiz, or maybe just some kind of office hours, informal office hours, and then Wednesday, Thursday it will be reviews. So I'll try to prepare some exercise that will cover the whole lectures, or at least as much as we can do in 2 hours worth of time. But yeah, don't worry. We won't be doing like a lot of new stuff next week on Wednesday and Friday, and then you'll have to review that and no discussions. But yeah. So basically, we should be almost done by this week, except for one last final lectures I want to do on Monday. But yeah. So yesterday we started talking about electrical currents, which describes how much charges how much charges are moving across a section per amount of time. And so we've seen that it's to get the electrical current, we just take the time derivative of the charge and we get the electrical current. And we've seen that we can also use electrical current per amount of surface area, which is the current density, G. And then we've seen a few properties, notably that it's oriented so that it assumes that positive charge are flowing, even though it's electrons that are flowing, but electrons are flowing in the other direction, positive charge would be flowing. And in the end, it just is equivalent. And yes, we've at the end of the lecture, we've expressed this electrical current using a reasoning of moving charges and assuming they move at a certain grid velocity we call VD. And we didn't give too much detail about VD and where it's coming from and why we can assume they move at a constant velocity VD. So today we'll start so yeah, we've seen that the current could be expressed as density multiplied by the charge, multiplied by the drift velocity, multiplied by the cross-section of your wire, for instance. And so today we're going to start addressing this drift velocity. So let's assume we have a conductor of length L. And in this conductor, we applying a potential difference V, for instance, with a battery or something like that drives a potential difference. And so because of this potential difference V, we have an electrical current E that arises. And if we assume this electrical current constant, they just V, it's the electrical field that arises just the potential divided by the length. And so because of this electric field, electrons that are free flowing in the conductor are going to be accelerated in the direction against the electric field. And so because of that, of the electrical force, they experience an acceleration associated with the electrical force, electrical field, and so it's just a charge multiplied by the electric field divided by the mass. And so if we were stopping there, then we would have electron that would be constantly accelerating under the influence of the electric field. But we said that we assumed that they were moving at a constant velocity. So there's something else that's adding complexity, and that's limiting this velocity. And what's happening is that as electrons are accelerated and move across the electric field, they will be randomly colliding with the ions that are not moving but are still there in the material. And when they hit the ion, when they collide with these ions, they are stopped or they are pushed in another direction, which is going to stop their momentum, their velocity. And so then they have to start again accelerating, but then they will hit another ion, collide with another ion, and lose their velocity along E, and so on and so on. And so we can kind of view these collision as a drag force, similar to the, for instance, the drag force of the air for a skydiver that's falling. Falling from an airplane. And you know, a skydiver falling from an airplane, even though the gravity would be constantly accelerating, making him constantly accelerate, the drag force from the air make him reach final terminal velocity that he cannot go faster, and that will remain constant. And that's the same for the electrons. The drag force associated with the acceleration force from the electric field converge to constant velocity that depends on the electric field and the material, and that will be our drift velocity. And so if we look at the overall behavior of the electron, it will move kind of in a hectic manner, moving up, down, even sometimes back, but average over many collisions, it's still going in the direction opposite to the electric field at velocity, average velocity, VD. And this velocity, drift velocity, is related to the electric field and a constant that depends on the material that's called the mobility. And so it just, for an electron, it's just minus because the charge of the electron is minus. So it's going in the opposite direction to the electric field. And then mu E, which is the mobility, multiplied by the electric field. And so this is the amplitude, but if we're considering the vector velocity, then it's just minus mu E, the mobility, multiplied by the vector electric field. And we see that it depends on the material, but also on the electric field. But with typical electric field we can reach in electrical circuits, this drift velocity is about 10.5 to the power minus 5 meters per second in a copper wire. And so this means that the electric field is pushing electrons in the wire, and that's what's causing the electrical current. But note that this velocity, all things considered, is pretty small, right? If you wanna do 1 meter, if the electron wanna do 1 meter, they'll take 10 10,000 seconds, so a few hours. And so that shows that when, for instance, at home, you're turning on the switch to turn on the light, you clearly see that it's not electrons that are, for instance, from the switch that are traveling up to your light, because if that was the case, turning a light would take several hours, but it's almost instantaneous. And that's because even though electrons are moving slow, there are electrons everywhere in your electrical circuits, in your wire. And so when your electrons are moving by, if you're turning on your electrical switch, then electrons start moving. But since they are everywhere, electrons that are close to your lamp are also moving. And so there's a current that's arise everywhere in the electrical circuit, because first electrons are pushing another one after them, and so on and so on. So that's what's happening, and not individual electrons that are traveling all along the circuits. So that's something to keep in mind. Okay, and so if we consider a conductor of length L and of cross section A, then by definition, this conductor will have a volume V equal to the cross section multiplied by the length. And so the total charge in this conductor of length L will be the total moving charge. So we're considering electrons here, just because that's electrons are contributing to the current. So we're considering only the charge associated with the electrons. So the total charge will be minus E, which is the charge of a single electron, multiplied by the density of electrons, which means the number of electrons per unit volume, and then just multiply by the volume of our conductor. So now let's look at the time required to move all of this charge out of the volume V. Then the time will be the length of the volume divided by the drift velocity, V drift, where we just express this drift velocity as a function of the electric field and the mobility of the electrons. And we've seen that the current is going to be the total amount of charge that's moving divided by this time it takes the electrons to move out of the volume. And so we have the charge that we expressed at the previous slide. So just basically the amount of charge multiply in the volume multiplied by the charge of an electron, and we divide by the time, which we just express here as the distance, the size of an element divided by the drift velocity. And so we see that the specific length of our conductor simplifies, and then we have something, we divide here, by the drift velocity, so it goes back up. And so we have this expression of the current here, and switching the drift velocity by its expression as a function of the electric field, we obtain that the electrical current associated with the electron can be expressed as a function of the electric field E and the density and mobility. And so we see here we have something that's kind of a constant associated with the material. So density of electrons, the mobility, and then something that's associated with the electrical state of the system, the electric field. And we can replace the electric field by its value, so the potential difference between the two edges of the conductor divided by the length of this conductor. And yeah, and you're right, there's A missing here. It's there on the slide after. So yeah, it was missing. Good catch. Uh, yes. So indeed, it depends on the cross-section area. And so, yeah, what I was saying, we have the material constant. So here, E and mu E, mobility. And so this is what we call the conductivity of the specific material. And we write it sigma. And then we have something associated with the geometry. So the length, wait. Yes, the length that comes from the electric field and a cross section that we just remembered to conserve. And so if we put those two together, this is a constant of the material and something associated with the geometry. And so we see that we have something that's still, I would say, a constant of a specific geometry and materials. Like if you build a wire or something, this will be a specific characteristic of this wire, which is, and we'll identify this as being the inverse of the resistance, because this is the conductivity, and so we'd be called the conductance or the inverse of the resistance. And so, by identifying this, calling it, this the resistance, because see that if the material is more conductive, this is larger, and so it means that R, the resistance, is smaller. We can identify this expression of the current being equal to the voltage divided by the resistance. And this, even if you haven't done any electricity courses or lectures, you might remember this because it's pretty common law, because it's Ohm's law, which describes how much current flows for a given voltage. So, and that depends on the resistance of the material to this flow of the current. So in a way, if we come back to our analogy with the fluid dynamics, the resistance would be kind of the viscosity in our system that makes the electrons having more troubles free flowing when we put a voltage difference between 2 points. Because this resistance is associated with the friction when the electron drifts at a constant velocity. And if we have an electrical system and we can measure both the voltage and the electrical current, then if we measure, then we can deduce the resistance obtained in our system. And so if we see, if we just analyze the expression of the resistance, we see that at the top we have volts, and at the denominator we have amperes. And so this is a new unit that's called ohm, or that's sometimes, that's also described as a capital omega here. And so, as we've seen, this resistance R really depends only on the material and the shape, the physical condition where this material is, that can affect the inner property of the material, but it doesn't depend on the electrical system. It's really a constant of the specific material and shape. So if you increase the voltage, you will also increase the current so that the resistance remain the same. So if we have a battery that's imposing a voltage V across a cylindrical wire that has a resistor of length L and a cross-section A. If we double the length of the resistor, but we attach it to the same battery, what happened to the drift velocity of the electron in the new resistor? And drift velocity Vd is equal to minus mu E, mu the mobility multiplied by the electric field. So all right. So mostly answered the choice number 2, saying it decreases, and that's correct because if we double the length of the resistor, but the voltage, imposed on both ends of the resistor is kept constant because it's given by the battery, then the electric field inside the resistor goes down because the electric field, if assuming everything is constant, is going to be the voltage divided by the length. And so keep the voltage constant but increase the length, the electric field goes down, and so the drift velocity goes down to all right. So now we have a similar situation where we have a battery and we have a resistor of length L and a cross-section area A. And now we keep the same length, but we double the cross-section of our resistor and still attach to the same battery. So what's happening to the drift velocity? Okay. So it's for those who answered, it's a draw between choice 2 and choice 3, 50% each. And the correct answer is stay the same because, again, if we take this electric field potential divided by length, here we don't change the potential, we don't change the length, so the electric field remains the same, and so the drift velocity remains the same. But we did change the cross-section area, and so the electric field, the current will increase because the cross-section is larger, but the basically they're just more electrons that are going through, that increase the current, but they're going at the same velocity. Okay, and yeah, yesterday I mentioned in some situation when we prefer using the current density instead of the current because sometimes there's there's not a well-defined space or it's not confined to a well-defined wire, and so it's more useful to have a vector current density where the current is defined per amount of area, and so just define just define the current density J to be the current I divided by the cross-section area. And so we just in the same expression, but without the cross-section. So we have E and E multiplied by the drift velocity. And so the vector current density is just E and E multiplied by the vector, the drift velocity vector V. Okay, and so now using what we use to derive Ohm's law for the electrical current, we can start from this expression where we have the conductivity multiplied by the geometry term multiplied by the potential. And so we see that now if we divide by A to get the current density, basically what we get this time, the area A cross section, it cancels out. And so we just have something expressed as the current density J is equal to the sigma, the conductivity multiplied by the electric field. And so if we take the vector version of this, it's just the current density sigma multiplied by the vector electric field E. And so this is another formulation of Ohm's law using the current density, which can be useful sometimes. Okay, I think we've seen this situation before. We have a steady current flow going through a section that has a changing cross section. And so what can we say about the electric field and conductivity in segment in in those two segments 1 and 2? We are not really worrying about the segment 3 right now. And yeah, I did not launch the poll. So okay, now you can answer. The right answer is the answer number 3 here. Because yeah, so the conductivity doesn't depend on the geometry. Conductivity is only a function of the material. So it's see the charge density and the mobility, which is something that depends on the specific material, but not the geometry. And so the conductivity doesn't change the material property between the two. But the electric field here, since I is constant, but J is equal to I divided by A. And so if we reduce the cross section, means that we're increasing the current density here. And we've seen that the current density is equal to sigma E. And so if we're increasing the current density here, we're also increasing the electric field in that section based on the current density Ohm's law. Okay, and so how, now let's imagine that, so we've seen the resistance of a material, for instance, a wire, it's just a constant of this specific wire. It's not just on the material, it also depends on the geometry, but we've seen that that the resistance was not depending on the voltage or the current in the system. It's just a constant of the material. So it means that if we are given a specific wire and we know its size, its material, we are able to compute its resistivity. And so the its resistance. And so its resistance is equal to rho, which is the resistivity. And it's just, the inverse of the conductivity, right? The more a material is resistive, the less it's conductive, and conversely. So just for the sake of considering the resistance, we invert the conductivity to get a resistivity, but they're describing the same thing, just depending on what we're considering, we prefer using the resistivity or conductivity. And then it's just a function of the geometry, so the length. So the more we have material, the more it's resistive. And in the denominator, we have the cross section. The larger the wire, the more conductive it is, and so the less resistive it is. And so that's how we get the resistance for a given material. And so we see it's very common for wires, pretty large wire to be made. If you cut them and look at them, they're actually made of many small wires, and it's so that way we can increase the area because you can sum all the areas of each wires, and so you get a smaller resistivity in your wires. And that's something that we want when we have a wires. We want the wires to freely transfer our electrical current without resisting, without dissipating. And so we want the wire to be as conductive as possible. And so that's why we tend to want to increase the area of those. And why not want to use a single larger wire? I mean, that's just a simple technical issue, is that if you have a single wide wire, it's going to be less flexible, more susceptible to break and damage than a lot of smaller wires that are put together. And so that's why we make larger wires using a stranded wire that are composed of many small wires. All right, and yeah, before we stop here for today, just to give you some numbers, some order of magnitude. So we see that the resistivity is equal, based on Ohm's law, resistivity is equal to the electric field divided by the magnitude of the current. And this is just a rewriting of Ohm's law. And so the resistivity of a material is given in Ohm meter. So it's not Ohm per meter, it's Ohm meter because it's Ohm it's Ohm per meter multiplied by the cross section. And so you get meter minus 1 multiplied by meter square from the area. And this is just the L, 1 over L. So that's how you get ohm meter. And you see that for conductors and typically copper that is widely used in the electrical infrastructure, you see that it's in the order of 10 to the minus 8 ohm per ohm meter, while insulator are, like for instance, glass is going to be in the range of 10 to 10 14. So it's like orders and orders of magnitude between conductors and insulators. All right, we can stop here. We'll continue tomorrow, and hope you have a nice rest of your day. And I'll see you tomorrow, guys.